In this video, we will represent real numbers using floating point binary notation. Modern computers use floating point binary to represent real numbers. Floating point binary are efficient in representing either large values, extremely small values, or values that require high degree of precision. If you have studied science before, floating point binary is the same as standard scientific notation. The x10 tells us these numbers are in decimal form. Let's take a look at this notation means. We will see how big this number is. The first part is the mantissa, and the second part is the exponent. The exponent tells us how many times we should move the decimal point at the right side of the mantissa. To convert this notation into a number we are familiar with, let's float the decimal point 15 times at the right side of the mantissa. And this will give us a number of 15. You can see that this is a very large number to deal with, since there are so many digits that will occupy the space of computer's memory. In this example, observe that the exponent is negative, so we will move the decimal point at the left side of the mantissa. Clearly, this shows that this is a very small fraction number. So how does this apply to the representation of real numbers in a digital computer? Imagine this 16-bit register inside a CPU. A register with 10 bits for the mantissa with yellow color and 6 bits for the exponent in green color. The mantissa is in 2's complement, and so is the exponent. An imaginary point is immediately located at right of the sign bit of the mantissa. Having this binary number with 0 in the sign bit indicates that this is a positive number in 2's complement. If the sign bit is a 1, we are looking at negative number here. We can also see that the exponent is positive because the leftmost bit is 0. A positive exponent indicates that the binary point should be floated at the right. If the leftmost bit was 1, instead we will have a negative exponent, indicating that the binary point should be floated to the left. To convert this into decimal, we first work on the exponent. In this case, it is positive 4. So we have something times 2 to the power of 4. Remember where the binary point is. Then we will float it 4 places to the right. So the result is impure binary. The trailing zeros are removed because they are insignificant. Then convert this into decimal. So we get 5.25. Let's have another example. Imagine this 16-bit register inside a CPU. A register with 10 bits on the left for mantissa and 6 bits on the right for exponent. The mantissa is in 2's complement and so is the exponent. Having this binary number with 1 in the sign bit indicates that this is a negative number in 2's complement. To convert this into decimal, we first work on the exponent. In this case, positive 3. So we have something times 2 to the power of 3. Remember where the binary point is, then we float it 3 places to the right. So the result is 1001.11 in pure binary. The trailing zeros are not included because they are insignificant. Then convert this into decimal. So we get negative 6.25. That wraps up our discussion, and thank you for watching.